Okay, just starting the high res camera again. Okay, so what does it mean exactly? It means at most about. H of n is at most about g of n for sufficiently large values of n. So for small values of n, h of n could be bigger, much bigger. Well, but quite a lot bigger. But then for sufficiently large n, it's not that much bigger. It's not more than a constant times bigger. So it could be like 5 times bigger. Then, let's not even talk about little o. So also, somebody just wrote little o. This is a big O, okay? And that changes. A big O and a little o are different. Okay, so that's at most about. And this is the one people use all the time. And I need to restart the timer. Otherwise, we don't get a high resolution reset start. Good. So let's do, but you see it's a set of functions. So when I say something like n is in big O of n squared, big O of n squared, big O of n squared is the set of functions h of n such that, some people write colon, some people write a bar, such that there exists n0 c greater than 0, such that for all n greater than or equal to n0, h of n is less than or equal to c times n squared. Okay, is this true? So is n in O of n squared is 53 times n in big O of n squared? Well, is there an n0 and a c such that for all n greater than or equal to n0, so yes, let's say, so for n0 equals 60, c equals 32, do we have, this is h, do we have 53 times n is less than or equal to 32 times n squared for n greater than or equal to 60? Yeah, I think so. Just a second. 60, yeah, this is true. Good, so we can choose n squared. So for all n greater than or equal to 60, this is true. Therefore, this is true. I hope this is true. Maybe I could have just chosen this to be like 600 to be sure. But okay, so that's what it means. So 53n is at most about n squared. Okay, what about big omega? Big omega, g of n, equals, well, this is at least about. This is the set of functions h of n such that there exists n0, c greater than 0, such that for all n greater than or equal to n0, h of n, you just turn the inequality sign around, right? Is going to c times g of n. Now, some people might move the c over, but that's fine. You just, like, we're choosing a positive constant, so you can just take the inverse. So it doesn't matter which side you write the c on. So, this just, okay, exactly the same thing. There exists an n for sufficiently large n, h of n isn't too much smaller, and notice that c doesn't have to be an integer. H of n isn't too much smaller than g of n. So it's at least about. Is that e equals 30? C, that was a c equals 32. Somebody asked if it was an e equals 32 or c equals 32. Yeah, it's this c. So just to show that two functions that some function is in big omega of another function, if you want to do it like really, really thoroughly, you show that you can choose an n0 and a c such that this holds. Okay, so for example, I want to say that n squared is in big omega 53n. And notice that we don't actually, usually you don't write a constant in here, a constant coefficient, because it just gets eaten by this c. So constants disappear, lower order terms disappear. This is very handy. Why? Well, does there exist? Yes, that we just showed. There is 60, and c is 32, and then n squared is, oh no, actually that didn't quite work. Okay, now I'm going to choose, n0 equals 60, but now I want to make everything, because I didn't flip the side of c, I'm going to choose c equals 1 over 32. Okay? Could it be contained in? Why does n squared equal big omega? Because n squared, for a sufficiently large n, is at least about 53n. N cubed is at least about. It's actually much bigger. N is in big omega of 53n. Square root n is not in big omega of 53n. Even 1,000 square root n is not in. And I went and wrote the equal sign again. In. It's a set. It's not a thing. Okay. So for example, you have 1,000 square root n is not in big omega of n. For small values of n, 1,000 square root n is going to be bigger than n. But for sufficiently large values of n, it's not. Okay. So then we get into okay. So the thing is, I'm going to zip through this, because if you want practice with big O, big omega, big theta, blah blah blah, you can get it other places. Okay, I'm supposed to teach it to you, but I'm actually supposed to teach you a lot in this semester. And I'm probably not good at this kind of stuff as the videos you can get from like Khan Academy. You can just find stuff on YouTube. This asymptotic notation is in all of the introductory algorithms courses. And so there are things I want to emphasize. Is it generally true that if f is in big O of g, then g is in omega f? Yes, this is true. So then you have theta of n, and I said that was about, and that's just the intersection. Oh, okay, let's say I want this to be g of n. That's the intersection of O of g of n, cap, intersection with omega g of n. Okay, so if some function is in theta g of n, it means it's at most about g of n and it's at least about g of n, so it's about g of n. Okay? And now we get to that, so little o, which is what we saw when we were talking about Simon's time is little o of my time. I'm probably getting some of these backwards, but like watch the Khan Academy stuff. I want to talk about, there's something people say that, again, drives me nuts. Like apostrophes or something. And that I really want to address, because that's, I think, more important than it's important to get this stuff down, but you can get this, you can practice this offline. It's more important that I tell you something that people seem to get confused about. Okay. So we want to say not just that Travis's time will be at least about Simon's time. We actually want to say the time Travis takes to run distance n is going to be a lot more than for a sufficiently large n, and regardless of a constant head starts and shoes and whatever, Travis is slower. Not at most as fast, or not at least as slow. Actually, just slower, really slower. So that's like saying little o of g of n is the set of functions h of n such that for all c greater than 0, so this is where it's starting to look more like an epsilon delta ball thing. For all c greater than 0, there exists an n0 such that, I should check this, because I think I didn't get this right when I wrote it up. Oh, no, yeah, I didn't need that. Yeah, okay. I don't need another form. There exists, no, I do need. Where did I write little o? Oops. Yeah, in the definition of little o in the course notes, it needs a for all n greater than or equal to n0. It's missing this part, so it actually needs 3 quantifiers. H of n is less than or equal to I think this one usually is just less than, but it doesn't matter. C times g of n. Right? So this is sort of like an epsilon delta ball thing. And it's saying that you choose any c you like that's greater than 0, then there is an n0 sufficiently large such that for any value larger than that, h of n is less than that fraction times g of n. So like you say, okay, is there a time when Simon's time is going to be 1/100th of Travis's time? And you say, okay, yes, for sufficiently you can take those n is 3, so saying that n to the 3/2 is in little o of n to the 7/4. This says, okay, is there a time for all sufficiently large values n, is there a time when this is going to be 100th of this for all values, regardless of constants? Yes, there is. It'll be 1/100th. You say, okay, what about c is equal to 1/1000? Is there a time when Simon's time, is there a distance for which, for any distance larger than that, Simon's time will be 1,000th of Travis's time? Yes, there is. For anything after a certain distance, Simon's time will be less than 1,000th of Travis. 1,000,000th? Is there a distance? No. I mean, Travis is going to be dead by the time he tries to run this distance. But is there a time such that, you know, for any distance longer than this, Simon's time will be 1,000,000th of Travis's time? Yes, there is. Okay, so this is saying, and not surprisingly, you can also just say that you can write this in terms of limits. Okay? And then little omega, as we said, like little omega is just flipping things around. So little omega of g of n is the set. And I went and wrote equals again here. Is the set h of n, and it's the same stuff, such that for all c greater than 0, there exists an n0 such that for all n greater than or equal to n0, h of n is greater than or equal to c. Yeah, I see how you thought it was an e times g of n. Is there, so this is just flipping things around and saying, is there a distance such that for any distance further than that, Travis's time will be at least 1,000 times Simon's time? Yes, there is. Okay, so again, you flip things around. Let me just check to see if there's anything I'm supposed to be saying in here. Yeah, you can do this in limits. There is sort of a set of relations about these things. Oh, one thing that I should say. Oh yeah, so g of n is in big O of g of n. G of n is in big omega of g of n. G of n is obviously in big theta of g of n. G of n is not in little o of itself, and g of n is not in little omega of itself. So I drew a Venn diagram for you, because everyone loves Venn diagrams. Maybe I should just open the new set of markers. Question? Question? Somebody has a question. What in here, h of n is less than or equal to g of n? Okay, the less than or equal, so this is why I don't like people writing the equal sign, because equality is reflexive. So if x equals y, then y equals x. But if n is in big O of n squared, then n squared doesn't have to be in big O of n. It's not. So really, just think of this as sets. Just if you want to stay straight, keep things straight, just sort of get used to these definitions. Or you can think of it in terms of limits. F of n is in little o of g of n if limit as f of n, limit as n goes to infinity of f of n over g of n is 0. Is big O that? Okay. Limit or check the book. So the Venn diagram. It's also all of this is in the lecture notes. The Venn diagram is. The Venn diagram is going to be bigger. Oh, it's going to be bigger. Slightly bigger. This is in the lecture notes as well. Okay, so this is big O of g of n. This is big omega of g of n. In the middle is theta. of G of n. This is little o of G of n. Notice it's a proper subset of big O of G of n. It's proper because it doesn't include this point here is G of n. And then this is little omega of G of n. Okay, so now notice that this isn't everything. Okay, because there can be things which are not big O and are not big omega of G of n. This messes some people up. For example, if you consider the functions yeah, I'm going to put an absolute value sign on these for that's hard to read because it's near the reflection. Okay. Let's suppose f of n equals n dot absolute value sine n. G of n equals n times absolute value of cosine n. Okay, what are these going to look like? Well, it's going to look sort of like boing, 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 boing. Okay, so that's going to be one of them. And then the other one, and you get stuff like this bouncing up and down. And another of them is going to be sort of boing, 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 boing. Now, because it's sine and cosine, when one of them is bouncing up, the other one is bouncing down. Okay? So is there a time when you can say, oh, the red line is, you notice at this point, the blue line is way bigger than the red line. But at this point, the red line is way higher than the blue line. You can't say that these things are not about, it's not like, ooh, for a sufficiently large n, they're within a constant factor of each other. Doesn't work. They're not theta. And it's not true that the red one is at most about, because they're at most about the blue line, because there are times when the red line is way higher. And it's not true that the opposite truth, it's not, the blue line is at most about the red line, because there are times when the blue line is way higher. For any, you can't, and more than a constant factor higher for any constant you happen to choose. You can't compare these like that. So for equality, you can have, okay, x is either less than y or x is equal to y. If you're talking about numbers, at least real numbers, x is less than y, x is equal to y, or x is greater than y. Okay, it's like, you know, these are the three possibilities. But here it's like, yeah, we just can't compare these. Even for large values, there's still, you know, there are times when one is bigger, there are times when the other is much bigger. Okay. Textbook, Khan Academy, actually, as this says in the lecture notes, one of the, Thomas Corman, who's one of the authors of CLRS, the first author actually, he also wrote he's also a co-author of the, I gave a link to it, of the lesson on asymptotic notation in Khan Academy. Okay, half an hour. So what I want to talk about is people often, in previous classes, people have said, I don't know where they get this, but they say big O is when you're talking about the worst case, and big omega is when you're talking about the best case. And that is not right, okay? It's quite confused. Big O is at most about, and big omega is at least about. And you can say at least about in the worst case or in the best case. You can say in the worst case, we're going to need, you're looking at, think about like how you would talk about like real life stuff. You're going to say, ooh, well, How long is it going to take us to drive from here to here, here to there? Well, in the worst case, you know, if the tire goes flat and, you know, this happens and it starts to rain, it's going to take us at least about a day. Yes, big omega is a lower bound and big O is an upper bound. So this is like, big omega is at least about and big O. So you can say it's going to take us at least about a day in the worst case. Maybe on a good day, it'll take us 2 hours. But, you know, on a really, really bad day, it takes at least about this much. That's something somebody could say. On a bad day, it will take at least this much time. You could also say, on a good day, it will take at most this much time. You know? So, I want to give an example. I'm not sure I'm going to get through the master theorem today. But I want to, because I want to do sorting on Wednesday, and then maybe I can teach that. Okay, and we start the little camera again.